I welcome all of you to the tutorial video number 2 on the topic 4 on mass conservation and Bernoulli's equation. The tutorial video 1 was presented for mass conservation and this tutorial 2 is on Bernoulli's equation. So in the tutorial 1, I had presented 3 example problems. So the first example problem corresponding to this topic will start with example 4.4. This corresponds to siphoning out petrol from a fuel tank. You might have commonly observed that if you want to take the petrol out from a fuel tank to some container, let us say a canister, then you basically take a flexible tube which is called as hose pipe, and one end of the hose pipe you dip it to the fuel tank, and then from your mouth you basically suck the petrol till you find that the flow has started in the pipe, and then immediately you put the other end of the pipe inside the petrol canister, and then once the flow has started, you make sure that the canister location is below the fuel tank, and then this leads to the filling of the canister, and this process is called as siphoning. So we'll take a problem corresponding to the transfer of petrol from a car to a canister. So this is as shown here. This is a car, and this is a fuel tank. This is a fuel tank. This is a petrol inside this fuel tank. This is a petrol tank. This is the hose pipe whose one end is dipped inside this tank, and from the other end, first we suck so that the petrol flow has started, and then immediately we dip it inside this canister. Note that you are given the capacity of this canister, which is 4 liter. Now in this problem, we are interested in 2 parameters. One is the filling time for this canister. Now to calculate the filling time, you are already given the capacity of the canister. So you are already given the volume of the canister, which is 4 liter. Now to calculate the filling time, if we obtain the volumetric flow rate of the petrol, which is coming from the pipe inside this canister. So if you know the volumetric flow rate of the petrol through this pipe, then we can, using the volumetric flow rate and the volume, you can calculate the filling time. Now to calculate the volumetric flow rate, you will be given the diameter of this pipe. So if you know the velocity, average velocity of the fluid in this pipe, then you can calculate the volumetric flow rate. Note that at this point too, the pressure is corresponding to the pressure inside the canister, and inside the canister the pressure is atmospheric. So P2 is atmospheric. We are taking the reference of the elevation from here, so Z2 is 0 and P2 is atmospheric, and the velocity, the average velocity of the fluid inside this pipe which is coming out from the pipe is U2, that is we will determine later. This point 1 which we are considering is at the free surface of the tank. Now at this here again, similar to canister, here in the canister you have atmospheric pressure. Here at the point which is the free surface of the petrol inside the tank, the pressure is atmospheric. Now the elevation Z1 is given to you in this problem, which I'll present later, and the velocity for the dynamic head. The velocity we are making an assumption that the petrol tank is large enough and the volumetric flow rate is small enough, so that when the flow starts, the rate of decrease of the level of this petrol inside this tank, which will give you the velocity. The velocity at point 1 we are considering it is negligible, so we are considering that the kinetic energy at 1 is negligible. Potential energy, the pressure flow energy corresponds to the pressure is atmospheric here. So kinetic energy is 0, pressure is atmospheric, and the elevation will be given to you as Z1. So in this problem, other than the filling time, another interest is to know what is, because when the when the petrol is passing through this pipe, note that since the petrol is considered incompressible, and since the cross section of the pipe is uniform, the area is constant. So if you use the formula A1 V1 is equals to A2 V2, since the area is constant, the average velocity of the fluid inside this pipe will be constant. If the average velocity of the petrol inside this pipe is constant, the kinetic energy is constant. However, you see that the height of the pipe is varying. So the potential energy of the petrol flowing through the pipe is changing. And along with the change in the potential energy, kinetic energy is constant, and you know that Bernoulli's equation is basically the law of conservation of mechanical energy, where the mechanical energy consists of three energies: flow energy, kinetic energy, and potential energy. So for flow in a pipe, kinetic energy is constant. So it's basically balance between the potential energy and the flow energy. So at the topmost point of the pipe, the potential energy is maximum, so the flow energy will be minimum, which will lead to the minimum pressure for the flow of petrol inside this pipe. And so the pressure is minimum at the maximum elevation or the potential energy point. And if this pressure is smaller than the saturation temperature corresponding to the atmospheric temperature in which you have a petrol, then there is a concern that there may be an evaporation here, and this evaporation will lead to formation of vapor bubble, and this vapor bubble can basically block the flow of petrol from the tank to the canister. So with this background, what is given to you in this problem is this Z2 is 0, Z1 and Z3 are given to you in this as follows. Z1 is 0.75 meter, Z3 is 2.75 meter. You are given the diameter of the pipe as 0.4 centimeter. The density of petrol is 750 kg per meter cube, and the volume of the canister 4 liter is 4 into 10 to the power minus 3 meter cube. What you have to determine, there are two things you have to determine. First is the filling time, and second is the pressure at maximum elevation, where you have maximum potential energy and minimum pressure, that is P3. So we start the solution. First, to determine the filling time. As I mentioned earlier, the pressure P1 is atmospheric. We are considering the velocity, the rate at which the level of the petrol is reducing. We are considering the size of the petrol tank as large enough, the volumetric flow rate in the pipe is small enough, so that the rate of change of level of petrol inside this tank is negligible. So which means U1 is negligible as shown here. And at P2, which is which corresponds to pipe outlet, the pressure is corresponding to the pressure inside the canister, which is atmospheric. So the P2 is atmospheric. Basically, we apply to calculate the filling time, we are interested to determine the velocity, the exit velocity for the pipe. So to determine that, we apply the Bernoulli's equation between 1 and 2. And the equation is presented in terms of, in the head form, P1 by rho Pg, where rho P is the density of the petrol, plus U1 square by 2G plus Z1 is equals to P2 by rho Pg. This is the pressure head, this is the kinetic head, and this is the elevation. So if you substitute P1 is equals to P1 is atmospheric here, and P2 is also atmospheric. So this two cancels down, and we are considering U1 close to 0. This also cancels down as shown here. U1 is close to 0, and P1 and P2 both are atmospheric, so they cancel down from the left hand side and the right hand side. And to calculate U2, you get a formula from this equation that U2 is equals to square root of 2G Z1 minus Z2 as shown here. And once you substitute Z1 is equals to 0.75 meter and Z2 is equals to 0, then you get U2 is equals to 3.84 meter per second. Once you know the velocity, to calculate the filling time, your interest is to determine the volumetric flow rate of the petrol which is coming out from this pipe. To calculate the volumetric flow rate, you have to multiply U2 is this exit velocity of the petrol. So that velocity, if you multiply by the area, cross-section area of this uh, hose pipe, which is pi by 4 dp square, the diameter is 0.4 centimeter. So if multiply with the area with U2, you get volumetric flow rate as shown here, which comes out to 0.053 liter per second. And using this volumetric flow rate and the volume of the canister, that is 4 liter. So to calculate filling time, note that this is a minimum filling time because, so as I said that in this case there are certain approximations. There is some frictional loss um, for the when the fluid is passing through this pipe. So the time that you get here is the minimum filling time. So as I said that Bernoulli's equation gives you certain limiting values for engineering problem. So to calculate the filling time, you basically take the ratio of the volume of the canister, and which is shown here. This is the volume of the canister, and divide by the volumetric flow rate. Once you do that, as shown here, which is 4 liter divided by 0.0753 liter per second, you get the minimum filling time as 53.1 seconds. This is the first part of the question. The second part of the question is we have to determine the pressure P3, which corresponds to the maximum potential energy, and here the pressure will be minimum. Now to obtain this, we will apply Bernoulli's equation between 2 and 3 as shown here. Now when you apply between 2 and 3, note that the velocity of the average velocity inside the pipe is uniform because is same because the cross section area is same. So you get U3 is equals to U2 as shown here. Note that the point 3 is the somewhere in between the pipe where you have maximum elevation, and point 2 corresponds to the exit of the pipe. So at 2 and 3, the velocity, the average velocity of petrol is same because the cross section area is same. And we are considering the petrol as incompressible. At P2, we know the pressure is atmospheric. When you apply Bernoulli's equation between 2 and 3, this is the Bernoulli's equation in head form. For this equation, you know P2 is atmospheric. You know U2 and U3 are same, so it will cancel down from the left hand side and right hand side. And your interest is to determine P3. So these terms cancel down, U2, U3, and P2 you substitute as atmospheric pressure. And from this equation, you can obtain P3, where you can see that it is less than the atmospheric pressure. And then when the pressure is less than the atmospheric pressure, we call this pressure as the vacuum pressure. P3 here comes out to be 81.1 kilopascal. Note that in this problem, the atmospheric pressure is 101.3 kilopascal, and the pressure at the maximum elevation P3, which is at this point of the pipe, the petrol inside this at this point has a pressure which is less than atmospheric by close to 20 kilopascal. And if this pressure is less than the saturation pressure corresponding to the operating temperature, then you can have evaporation, and then you can have a blockage as I mentioned earlier. And this P3 is a vacuum pressure. So this completes this problem. Now let us go to the next problem. The next problem corresponds to velocity measurement by a pitot tube. Basically, the pitot tube is a tube which is used to measure the velocity by placing this in uh, in an internal flow situation. So let me show you. Let us suppose this is a flow in a pipe, and then in this there are two tubes that you will see. One tube is inserted, which is flushing on the surface of the pipe. So what happens to this tube? This tube is called as piezometer. What happens to this tube is that the fluid which is close to the surface of the pipe, note that this pipe is stationary. So the fluid which is in contact with the pipe, since the fluid is stationary, since the pipe is stationary, the fluid will also be stationary. So this vertical pipe measures the pressure of the fluid which are sticking to the wall. This is called as piezometer. There is another tube. This is a vertical tube which is flushing the surface of the pipe. There is another tube which is of U shape, and it which is inclined at an angle of 90 degree, and this is inserted inside this pipe. So in this tube is called as pitot tube. Note that, so as I had discussed in fluid statics, due to the pressure, the if the water is flowing through this pipe, it will rise on this tube. Now the level of rise in this tube and in this tube, you see a difference. There is a larger rise in this case, because what happens in this case is, if you consider a streamline as shown here, so this is a streamline, this streamline we are considering along the center line of the pipe, where the velocity is uc. So on here, the streamline is horizontal, so along a streamline we'll apply the Bernoulli's equation. What happens is that if you consider the liquid inside this pitot tube, the liquid inside this pitot tube is stationary. So, and at point 1, the fluid is moving with some velocity. Now, when the fluid moves from fluid particle moves along the streamline from 1 to 2, since it realized that in this pitot tube, the fluid is stationary, it starts decelerating, and at this point, it's called a stagnation point. The fluid comes to rest. So its kinetic energy is slowly reducing. The height is same, so the potential energy is same. So when the kinetic energy is reducing, then the flow energy corresponding to pressure should increase. So here, the pitot tube measure a pressure which corresponds to static pressure plus dynamic pressure, which dynamic pressure corresponds to the pressure that is generated when you decelerate a fluid particle from certain velocity by an isentropic process. So static pressure plus dynamic pressure is called a stagnation pressure, and that stagnation pressure is measured by this pitot tube. This piezometer measures the static pressure. So we will consider the static pressure as well as dynamic pressure, and using this two pressure we'll finally we'll obtain an expression which will basically take the difference in the level between the two tubes, and will obtain the velocity of the fluid at the center line of this pipe, which is denoted here by UC. Note that our objective is to measure this UC, which is the velocity at the center line of the pipe, using the level of liquid rise in piezometer and the pitot. This is the pipe in which water is flowing. This is a piezometer, and this is a pitot tube. These are the level of which are given to you. So from the center line to the wall, the distance is h1 as shown here, and the rise in the level in the piezometer is h2, and the difference in the level of the piezometer and pitot tube is h3. These are the three heights which we'll be using to measure the velocities. To derive an equation for measuring the velocity, so you are given h1 is equals to 3 centimeter, h2 is equals to 7 centimeter, h3 is equals to 12 centimeter. And what you have to determine is this center line velocity. So to obtain the center line velocity, we'll be considering 2 points 1 and 2 as shown here along a streamline at the center of the pipe. So when we apply the Bernoulli's equation, since this streamline 1 to 2 is horizontal, so the elevation is constant, potential energy is constant. So this Z1 and Z2 is same and it cancels down. Now I have also mentioned at point 2 the velocity becomes 0. So U2 will be 0. Z1, Z2 cancels down and U2 becomes equals to 0 as shown here. Now U2 become equal to 0 and this U1 I have mentioned that this U1 is equals to the center line velocity which is UC. So we substitute it as UC. So then you get UC square by 2 is equals to P2 minus P1 divided by rho G. Now this P1, P2 you can obtain. P1 is a static pressure that you can obtain by considering this level, which is P1. To calculate P1, you will basically take rho H1 plus H2, and to calculate P2, it will be equal to rho H1 plus H2 plus H3 as shown here. Now if you take the difference of this two pressure, P2 minus P1, you will basically get rho G H3. So if you substitute rho G H3 here, rho G cancels down from the numerator and denominator and you get H3 here. So UC will be square root of 2G H3 as shown here. And UC comes out to be 1.53 meter per second. So to derive this expression for the velocity at the center line, I have shown you that we need H1, H2, H3. But finally, the final expression that we have derived, know that it involves only H3, not H1, H2. And what is this H3? H3 is the difference in the level of the free surface in a piezometer and a pitot tube. Okay, so if you measure the level difference as shown here, H3 is the difference of level between the pitot tube and the piezometer. So once you measure this difference, you can measure the velocity or flow in a pipe. Right now I have shown you at center line, but you can also obtain this at various radius corresponding to the pipe. And then you can also finally obtain the velocity profile at a particular axial location for flow in a pipe. The last problem that is being considered for this tutorial video on Bernoulli's equation is rise of ocean due to a cyclone. Cyclone we have recently experienced in the month of May and June. We have experienced two cyclones in India. The first one in May was name of the cyclone was Amphan, and the second, which was on Bay of Bengal, and the second we experienced in the beginning of the June. These two cyclones were within 2 weeks gap. The second cyclone was called as Nisarga, and it was in the Arabian Sea. The first one was on Bay of Bengal, the second was on Arabian Sea. Now this cyclone is basically it's a large mass of circulating air where it's like a spiraling inward flow, and in the northern hemisphere the inward spiraling flow is counterclockwise, whereas in the southern hemisphere the inward spiraling flow in a cyclone is clockwise. The difference is due to the Coriolis effect. India is in the northern hemisphere, so let us consider a situation where the cyclone is the source of the cyclone is basically, let us you in an ocean, if you have a locally a very low pressure region, let us suppose this is a point which is at this point, let us say pressure is atmospheric, and at this point let us say pressure is below atmosphere. So if it so happens and that in ocean at certain portion of the free surface the pressure is atmospheric, at some other free surface, let us say here, the pressure is less than, so if you have a low pressure region, so if there is a low pressure region, the water column rises, and since you have a large pressure here and small pressure here, the nearby wind gets sucked up here, and there is a circulation which gives rise to a These are the 3 points which are shown. So the rise in the water level is due to low pressure. So at 2 and 3, note that you have a low pressure, pressure less than atmospheric. So you have a vacuum pressure, and this low pressure leads to inward spiraling flow of the large mass of air. Note that it's a very large mass of air. Just to tell you, in this problem, the distance between 1.1 and zero point 0.3 is 350 kilometer. So it's a you can imagine the size of the cyclone. So this I had considered corresponding to, let us say, in India, which is in northern hemisphere. So you have anti-clockwise spiraling flow as shown here, and so this is your cyclone. This is the ocean. This is the cyclone, and the center of the cyclone is called as eye. So this is the eye of the cyclone. Now, typically, when you consider the center of the cyclone or center of a vortex, the velocity here is very small. But as you keep moving out, the velocity increases. One of the characteristics of a cyclone is that it has a very large wind velocity. So let us suppose at this point the velocity is the maximum velocity in the cyclone. In this case, it's 250 kilometer per hour. So there are 2 points which are given to you. So these are the height of the water, the rise in the level in the ocean, which are given at 2 points, 2 and 3, which are corresponding to subatmospheric pressure or low pressure or vacuum pressure. And as I mentioned, the distance between the eye and this free surface, which is at atmospheric pressure, it is 320 kilometer. And at one, you have a calm ocean level. The level is not rising. The pressure is atmospheric. Whereas at 320 kilometer away, which is this point 3, the pressure is low. So when 320 kilometer away, the pressure is low, and at this location it is atmospheric. This low pressure leads to the suction of large mass of the air, and you have an inward spiraling flow of air, which is called a cyclone. And depending on the maximum velocity of air in a cyclone, you have 5 different classes of cyclone. Just to give you an idea, the maximum velocity of cyclone for the cyclone Amphan that we had in the middle of May, which was in Bay of Bengal and severely affected Kolkata, the maximum velocity was 260 km per hour, which is called as class 5 of the cyclone. And another cyclone that came to Mumbai from Arabian Sea, the cyclone was in Arabian Sea. The maximum velocity of the cyclone in the cyclone was maximum velocity of air in the cyclone was 110 km per hour. So this 110 km per hour maximum wind velocity, this comes in the class 1 of the cyclone. So as the class increases, the maximum velocity of wind in the cyclone is more. And this larger wind velocity basically causes the increase in the kinetic energy. Now this increase in the kinetic energy leads to decrease in the flow energy. That is basically, it further reduces the pressure. At point 3, let us suppose you already have a low pressure. This is corresponding to the eye of the cyclone. So at 3, there is already a low pressure which leads to this cyclone. But due to the large wind velocity, there is a dynamic pressure which is generated. Let us suppose at this point 2, as I mentioned, let us take this point 2 and 3 in air if you consider in cyclone. What I'm saying is at the eye, which is corresponding to like a center of the vortex, the velocity is very small. So the velocity at the eye, which is UV, is close to 0. Whereas the maximum wind velocity, let us suppose is at this point. So at this point, you have a large maximum wind velocity in the cyclone is, let us say, 250 kilometer per hour, which is corresponding to the class 5 of the cyclone. So when you have a large wind velocity, you have a large kinetic energy. Now these 2 points have same potential energy. Now here the kinetic energy, if you compare the kinetic energy, here you have a much larger kinetic energy. So on the straight line, here we are assuming that the flow is irrotational, which is a big assumption, especially for a cyclone. But even then, we can get a good approximation, or I would say first approximation, or the maximum. Basically, we are interested in, due to this dynamic head, there is a further increase in the level of the height. So we're basically interested in H2 minus Hd. We are interested in this problem that this maximum velocity of the cyclone, 250 meter per second, basically the increase in the kinetic energy here as compared to the kinetic energy at B causes the reduction in pressure here. So the sea that has locally had a low pressure, but due to this large wind velocity, the pressure reduces further at this point, and there is a further increase in the level of the water in this ocean. From fluid statics, you know that at certain location, if the pressure is let us say atmospheric, and if you have another location you have sub-atmospheric pressure, then if you draw a horizontal line from here, then everywhere the pressure should be atmospheric. So if the pressure is subatmospheric at some location, then the level of water has to rise to for the balance in the pressure. Okay, so whenever in an ocean, if the pressure is, let us suppose, uniform, then the level of ocean is uniform. However, in certain locations which are, note that this dimension which we are considering is in hundreds of kilometers. If hundreds of kilometers away in an ocean, at some location above the free surface, if the pressure is locally, there are certain phenomena that happens that leads to the reduction in the pressure above the free surface. This reduction in pressure causes increase in the level of water. Now the danger of this cyclone is that this rise in the level of water has happened in ocean, in the middle of the ocean. But the danger with this cyclone is basically carry, they they drive this column, or the wall of the water towards the shore. This cyclone, they travel from the middle of the ocean where you have low pressure region to the towards, let us suppose, to the seashore. Let us suppose they are coming to Mumbai. So from the middle of ocean, this cyclone takes this column of, or this wall of water from the middle of the sea towards the city of Mumbai. And the danger of the cyclone is that it drives this column of water, and when it hits to the seashore, then there is a danger of, you have destruction, as well as, because you have both large wind velocity as well as the large height of the water column, which it basically falls on the seashore. So with this background, let us start with this problem. What is given to you is the pressure at P1, which is atmospheric. Here the pressure is given in terms of millimeter of Hg. So basically you are given in terms of the height of mercury. Hg corresponds to mercury. So to calculate the pressure, you multiply this 762 with the density of mercury. This is the height. So basically you multiply rho g h. H is 762 millimeter. Rho, you will take the density of Hg, mercury, and multiply by g. The pressure at the eye is given to you. You are given P1 and P3. The pressure at the eye is given as 560 mm of Fg. The density of sea water is given as 1025 kg per meter cube. Note that the density of the water normal water that we consider is 1000 kg per meter cube. Sea water is 1025 kg per meter cube. Density of mercury is 13,600 kg per meter cube. It's much heavier. The density of air at atmospheric pressure, it is 1.2 kg per meter cube. So note that the density of air here is 1.2 kg per meter cube. But the density of air here, 3, where you have subatmospheric pressure, the density will be different. If we assume that the temperature of the water in the ocean is uniform, almost uniform, then if you apply ideal gas equation, P is equals to rho RT, so here you have a low pressure, so density is directly proportional to pressure. So if you have a low pressure, you will have a smaller density. So using this rho A and this P1, P3, we will later on determine the density of air at this location. In this problem, we have to basically determine the height of this liquid water column H1 and H2 and H3. First, we will determine H3. For that, we'll apply the Bernoulli's equation between 1 and 3 as shown here. So we are basically considering the density of seawater in the Bernoulli's equation. Now, in this Bernoulli's equation, we will at P1, this P1 is corresponding to 762 mmHg, which is given to us, which is atmospheric pressure. Here we'll make an approximation that at the free surface of this sea, the change in the velocity is negligible. So we'll assume U1 is equals to U2 is equals to U3. So with this assumption, the kinetic energy on the left hand side and right hand side, it will cancel down. And basically the difference in the level will correspond to the difference in the pressure between 1 and 3. So here you have an atmospheric pressure, you have subatmospheric pressure. So here the flow energy is less, so there should be a larger potential energy. So kinetic energy, since we have assumed U1 is equals to U2, kinetic energy is same. And you have a sublet pressure is less, so flow energy is less, so the potential energy has to increase, so you have a larger height here. So with this background, the kinetic energy cancels down from both the sides, and the Z1 is 0, and you get H3 is equal to P1 minus P3 divided by density of seawater into G. Now this P1 minus P3, I have mentioned that this is given in terms of millimeter of Hg. So P1 minus P3 will be density of Hg, rho Hg multiplied by G, 762 minus 560, as shown here. G will cancel down from the numerator and denominator. So this G will cancel down and you will get the ratio of the density rho of Hg divided by rho of seawater. And you will have the difference of the column of the Hg that was mentioned for the pressure. And if you substitute the density of Hg, mercury, that is 13,600, the density of seawater is 1,025, and the difference in the level of P1 minus P3, this 2,202 multiplied by 10 to the power minus 3. It is in mm, so that's why this is 10 to the power minus 3. So finally you obtain H3 as 2.68 meter. Just imagine the height of the water column due to the low pressure somewhere in the middle of the sea. So this is the first thing. The second thing that we want to obtain is that due to this cyclone, as I mentioned, this 3 corresponds to the eye of the cyclone where you have low velocity, whereas not, so air velocity is low, but far away there is a maximum velocity in the cyclone. Let us suppose this is the point A, and due to at this point A there will be a large kinetic energy. So as compared to B, A and B, they are at same elevation, so potential energy is same. However, at A you have a much larger kinetic energy. So much larger kinetic energy will lead to reduction in pressure here. That is what we will obtain. But first we will obtain a relationship to calculate H2. We will obtain first a relationship between P2 and P3. So we obtain Bernoulli's equation between P2 and P3. Now this Z2 is H2 and Z3 is H3 for the present problem. the velocity of water at the free surface, we have taken u1 is equals to u2 is equals to u3 as shown here. This u2, u3 will cancel down, so kinetic energy is same in the free surface. And basically, the difference of pressure, as in the previous Bernoulli's equation that we had applied between 1 and 3. So the difference in the level is basically coming due to the pressure difference. So you get an expression for H2 minus H3 is equals to P3 minus P2. But we are given P1 and P3, but we are not given P2. So we don't know P2. So what we do is that we apply Bernoulli's equation. So if you draw a vertical line from here, which corresponds to the I, and if you draw a vertical line, it comes to a point where you have a maximum velocity of the cyclone. And if you join these two by a straight line, so what we say is that we will apply Bernoulli's equation and we will obtain the pressure here, and we are assuming that the pressure here is equals to pressure here. So PB is equals to P3. PA we are assuming it to be equal to P2. So to calculate this P2, we basically apply the Bernoulli's equation between A and B. Note that till now 1, 2, 3, whatever we were taking corresponds to the free surface of the sea, which is corresponding to water. Now this A and B is corresponding to air. So earlier, the density that was presented in the Bernoulli's equation was corresponding to seawater. Now for air, you have a rho A. Now this rho A we will be considering corresponding to the point 3, which is subatmospheric pressure. We are given the density of air at so this rho A is corresponding to 1. Now here you have low pressure and air is compressible, so the density is varying. So we will apply ideal gas equation and obtain the density at point 3, and that density is presented here. Now between A and B, the potential head is, we are considering A and B on a horizontal line. So the level is same, so the potential energy is same for air. So this ZA, ZB cancels down from the left hand side and right hand side. You are given that the velocity at the I, UB is close to 0, so it will cancel down. So this is 0, ZA, ZB cancels down. I have mentioned that we are assuming PA is equals to P2 and PB is equals to P3. So if you do that, you get an expression as P3 minus P2 is equals to rho UA square by 2. So if you substitute this P3 minus P2 as shown below as rho A U square by 2, so you get H2 minus H3 as rho A UA square by 2 rho HWG as shown here. Now, you are given the density of air at atmospheric pressure. However, we are applying it between A and B, and we know at B, we know the pressure, we don't know the pressure at A. So from using the pressure at B, which is a subatmospheric pressure, first we will use ideal gas equation, where we are considering that the temperature is uniform between A and B. We will basically consider density directly proportional to pressure, and using, as I said, P is equals to rho RT at constant temperature. We know that at P1, which is atmospheric pressure, you are given the rho at standard operating temperature and pressure, which is 1.2 kg per second. At P3, we know this pressure. We'll use this expression to calculate the density of air. So once we do that, we get the density of air as 0.882 kg per meter cube. So the density, you can see that at atmospheric pressure, it is 1.2 kg per meter cube. But at subatmospheric low pressure, vacuum pressure, the density of air has reduced to 0.882 kg per meter cube. This density will be used here, and the density of seawater is given to you. The velocity UA is given to you, it is 250 km per hour. To convert it into meter per second, we'll divide this by 3.6. So H2 minus H3 is finally obtained as shown here, where you substitute rho A by rho SW. This UA square, 250 km per hour, to convert in meter per second, you divide by 3.6 and take it square and divide it by 2g. Once you do that, you can see that due to this dynamic, uh, due to this large velocity in a cyclone, the the large velocity leads to the this increase in the height 3 is not due to cyclone. Note that the increase in the height due to the cyclone is H2 minus H3. That's why here I am emphasizing H2 minus H3. So due to the cyclone, the increase in the height is 0.21 meter. Now this H3 is given to you that we have obtained in the part A of this problem, which is corresponding to 2.68 meter. So if you substitute H3 is equal to 2.68 meter, you get H2 is equal to 2.68 plus 0.21, which is as shown here. So H2 is equal to 2.89 meter. However, note that this 0.21 corresponds to the dynamic head, and I have mentioned that this is just one of the observation that the cyclone, the large velocity in the cyclone leads to the further increase in the height of the water column in the middle of the sea. But the real danger of the cyclone is basically this cyclone, when it moves from the middle of the sea to the seashore, it carries this water column along with it, and when this large wind velocity along with a large column of uh, seawater, when it hits at the shore, it causes destruction in the cities which are near to the sea, such as Mumbai and Kolkata, that we had recently observed. Just to remind you, at Kolkata, the largest wind speed of the cyclone was 260 km per hour. That's a class 5 of cyclone. In Mumbai, the maximum velocity of the Nisarga cyclone was 110 km per hour, which is the class 1 of the cyclone. With this, I had come to the end of this tutorial video. Thank you for it.